spaCy is a modern Python library for industrial-strength natural language processing. In this free and interactive online course, you'll learn how to use spaCy to build advanced natural language understanding systems using both rule-based and machine learning approaches. Hi, I'm Ines. I'm one of the core developers of spaCy, a popular library for advanced natural language processing in Python. In this lesson, we'll take a look at the most important concepts of spaCy and how to get started. At the center of spaCy is the object containing the processing pipeline. We usually call this variable NLP. For example, to create an English NLP object, you can import the English language class from spacy.lang.en and instantiate it. You can use the NLP object like a function to analyze text. It contains all the different components in the pipeline. It also includes language-specific rules used for tokenizing the text into words and punctuation. spaCy supports a variety of languages that are available in spacy.lang. When you process a text with the NLP object, spaCy creates a doc object, short for document. The doc lets you access information about the text in a structured way, and no information is lost. The doc behaves like a normal Python sequence, by the way, and lets you iterate over its tokens or get a token by its index. But more on that later. Token objects represent the tokens in a document, for example, a word or punctuation character. To get a token at a specific position, you can index into the doc. Token objects also provide various attributes that let you access more information about the tokens. For example, the .text attribute returns the verbatim token text. A span object is a slice of the document consisting of one or more tokens. It's only a view of the doc and doesn't contain any data itself. To create a span, you can use Python's slice notation. For example, 1:3 will create a slice starting from the token at position 1 up to, but not including, the token at position 3. Here you can see some of the available token attributes. I is the index of the token within the parent document. Text returns the token text. Is-alpha, is-punct, and like num return Boolean values indicating whether the token consists of alphabetic characters, whether it's punctuation, or whether it resembles a number. For example, a token 10, 10, or the word ten, T-E-N. These attributes are also called lexical attributes. They refer to the entry in the vocabulary and don't depend on the token's context. Let's see this in action and process your first text with spaCy. Let's add some more power to the NLP object. In this lesson, you'll learn about spaCy's statistical models. Some of the most interesting things you can analyze are context-specific. For example, whether a word is a verb or whether a span of text is a person name. Statistical models enable spaCy to make predictions in context. This usually includes part-of-speech tags, syntactic dependencies, and named entities. Models are trained on large datasets of labeled example texts. They can be updated with more examples to fine-tune their predictions. For example, to perform better on your specific data. spaCy provides a number of pre-trained model packages you can download using the spaCy download command. For example, the EN Core Web SM package is a small English model that supports all core capabilities and is trained on web text. The spaCy.load method loads a model package by name and returns an NLP object. The package provides the binary weights that enable spaCy to make predictions. It also includes the vocabulary and meta information to tell spaCy which language class to use and how to configure the processing pipeline. Let's take a look at the model's predictions. In this example, we're using spaCy to predict part-of-speech tags, the word types in context. First, we load the small English model and receive an NLP object. Next, we're processing the text, "She ate the pizza." For each token in the doc, we can print the text and the .pos underscore attribute, the predicted part-of-speech tag. In spaCy, attributes that return strings usually end with an underscore. Attributes without the underscore return an integer ID value. Here, the model correctly predicted ate as a verb and pizza as a noun. In addition to the part-of-speech tags, we can also predict how the words are related. For example, whether a word is the subject of the sentence or an object. The .dep underscore attribute returns the predicted dependency label. The .head attribute returns the syntactic head token. You can also think of it as the parent token that this word is attached to. To describe syntactic dependencies, spaCy uses a standardized label scheme. Here's an example of some common labels. The pronoun she is a nominal subject attached to the verb, in this case to ate. The noun pizza is a direct object attached to the verb ate. It is eaten by the subject, she. The determiner the, also known as an article, is attached to the noun pizza. Named entities are real-world objects that are assigned a name, for example, a person, an organization, or a country. The doc.ends property lets you access the named entities predicted by the model. It returns an iterator of span objects, so we can print the entity text and the entity label using the .label underscore attribute. In this case, the model is correctly predicting Apple as an organization, UK as a geopolitical entity, and $1 billion as money. A quick tip: to get definitions for the most common tags and labels, you can use the spaCy.explain helper function. For example, GPE for geopolitical entity isn't exactly intuitive, but spaCy.explain can tell you that it refers to countries, cities, and states. The same works for part-of-speech tags and dependency labels. Now it's your turn. Let's take a look at spaCy's statistical models and their predictions. In this lesson, we'll take a look at spaCy's matcher, which lets you write rules to find words and phrases in text. Compared to regular expressions, the matcher works with doc and token objects instead of only strings. It's also more flexible. You can search for texts, but also for other lexical attributes. You can even write rules that use the model's predictions. For example, find the word duck only if it's a verb, not a noun. Match patterns are lists of dictionaries. Each dictionary describes one token. The keys are the names of token attributes, mapped to their expected values. In this example, we're looking for two tokens with the text iPhone and X. We can also match on other token attributes. Here, we're looking for two tokens whose lowercase forms equal iPhone and X. We can even write patterns using attributes predicted by the model. Here, we're matching a token with a lemma by plus a noun. The lemma is the base form, so this pattern would match phrases like buying milk or bought flowers. To use a pattern, we first import the matcher from spaCy.matcher. We also load a model and create the NLP object. The matcher is initialized with a shared vocabulary, NLP.vocab. You'll learn more about this later. For now, just remember to always pass it in. The matcher.add method lets you add a pattern. The first argument is a unique ID to identify which pattern was matched. The second argument is an optional callback. We don't need one here, so we set it to none. The third argument is the pattern. To match the pattern on a text, we can call the matcher on any doc. This will return the matches. When you call the matcher on a doc, it returns a list of tuples. Each tuple consists of 3 values: the match ID, the start index, and the end index of the matched span. This means we can iterate over the matches and create a span object, a slice of the doc at the start and end index. Here's an example of a more complex pattern using lexical attributes. We're looking for 5 tokens. A token consisting of only digits, 3 case-insensitive tokens for FIFA, World, and Cup, and a token that consists of punctuation. The pattern matches the tokens 2018 FIFA World Cup : In this example, we're looking for 2 tokens. A verb with the lemma love followed by a noun. This pattern will match love dogs and love cats. Operators and quantifiers let you define how often a token should be matched. They can be added using the OP key. Here, the question mark operator makes the determiner token optional, so it will match a token with a lemma by and an optional article and a noun. OP can have one of 4 values. An exclamation mark negates the token, so it's matched 0 times. A question mark makes the token optional and matches it 0 or 1 times. A plus matches a token 1 or more times. And finally, an asterisk matches 0 or more times. Operators can make your patterns a lot more powerful, but they also add more complexity, so use them wisely. Token-based matching opens up a lot of new possibilities for information extraction, so let's try it out and write some patterns. Welcome back! Now that you've had some real experience using spaCy's objects, it's time for you to learn more about what's actually going on under spaCy's hood. In this lesson, we'll take a look at the shared vocabulary and how spaCy deals with strings. spaCy stores all shared data in a vocabulary, the vocab. This includes words, but also the label schemes for tags and entities. To save memory, all strings are encoded to hash IDs. If a word occurs more than once, we don't need to save it every time. Instead, spaCy uses a hash function to generate an ID and stores the string only once in the string store. The string store is available as nlp.vocab.strings. It's a lookup table that works in both directions. You can look up a string and get its hash, and look up a hash and get its string value. Internally, spaCy only communicates in hash IDs. Hash IDs can't be reversed though. If a word is not in the vocabulary, there's no way to get its string. That's why we always need to pass around the shared vocab. To get the hash for a string, we can look it up in nlp.vocab.strings. To get the string representation of a hash, we can look up the hash. A doc object also exposes its vocab and strings. Lexemes are context-independent entries in the vocabulary. You can get a lexeme by looking up a string or a hash ID in the vocab. Lexemes expose attributes, just like tokens. They hold context-independent information about a word, like the text or whether the word consists of alphabetic characters. Lexemes don't have part-of-speech tags, dependencies, or entity labels. Those depend on the context. Here's an example. The doc contains words in context. In this case, the tokens I, love, and coffee, with their part-of-speech tags and dependencies. Each token refers to a lexeme, which knows the word's hash ID. To get the string representation of the word, spaCy looks up the hash in the string store. This all sounds a bit abstract, so let's take a look at a vocabulary and string store in practice. Now that you know all about the vocabulary and string store, we can take a look at the most important data structure, the doc and its views, token, and span. The doc is one of the central data structures in spaCy. It's created automatically when you process a text with the NLP object, but you can also instantiate the class manually. After creating the NLP object, we can import the doc class from spaCy.tokens. Here we're creating a doc from 3 words. The spaces are a list of Boolean values, indicating whether the word is followed by a space. Every token includes that information, even the last one. The doc class takes 3 arguments: the shared vocab, the words, and the spaces. A span is a slice of a doc consisting of 1 or more tokens. The span takes at least 3 arguments: the doc it refers to and the start and end index of the span. Remember that the end index is exclusive. To create a span manually, we can also import the class from spaCy.tokens. We can then instantiate it with a doc and the span's start and end index, and an optional label argument. The doc.ends are writable, so we can add entities manually by overwriting it with a list of spans. A few tips and tricks before we get started. The doc and span are very powerful and optimized for performance. They give you access to all references and relationships of the words and sentences. If your application needs to output strings, make sure to convert the doc as late as possible. If you do it too early, you lose all relationships between the tokens. To keep things consistent, try to use built-in token attributes wherever possible. For example, token.I for the token index. Also, don't forget to always pass in the shared vocab. Now let's try this out and create some docs and spans from scratch. In this lesson, you'll learn how to use spaCy to predict how similar documents, spans and tokens are to each other. You'll also learn how to use word vectors and how to take advantage of them in your NLP application. spaCy can compare two objects and predict how similar they are. For example, documents, spans, or single tokens. The doc, token, and span objects have a dot similarity method that takes another object and returns a floating point number between 0 and 1, indicating how similar they are. One thing that's very important, in order to use similarity, you need a larger spaCy model that has word vectors included. For example, the medium or large English model, but not the small one. So if you want to use vectors, always go with a model that ends in MD or LG. You can find more details on this in the models documentation. Here's an example. Let's say we want to find out whether two documents are similar. First, we load the medium English model, EN Core Web MD. We can then create two doc objects and use the first doc's similarity method to compare it to the second. Here, a fairly high similarity score of 0.86 is predicted for I like fast food and I like pizza. The same works for tokens. According to the word vectors, the tokens pizza and pasta are kind of similar and receive a score of 0.7. You can also use the similarity methods to compare different types of objects. For example, a document and a token. Here, the similarity score is pretty low and the two objects are considered fairly dissimilar. Here's another example comparing a span, pizza and pasta, to a document about McDonald's. The score returned here is 0.61, so it's determined to be kind of similar. But how does spaCy do this under the hood? Similarity is determined using word vectors, multi-dimensional representations of meanings of words. You might have heard of word2vec, which is an algorithm that's often used to train word vectors from raw text. Vectors can be added to spaCy's statistical models. By default, the similarity returned by spaCy is the cosine similarity between two vectors, but this can be adjusted if necessary. Vectors for objects consisting of several tokens like the doc and span default to the average of their token vectors. That's also why you usually get more value out of shorter phrases with fewer irrelevant words. To give you an idea of what those vectors look like, here's an example. First, we load the medium model again, which ships with word vectors. Next, we can process a text and look up a token's vector using the dot vector attribute. The result is a 300-dimensional vector of the word banana. Predicting similarity can be useful for many types of applications. For example, to recommend a user similar texts based on the ones they have read. It can also be helpful to flag duplicate content, like posts on an online platform. However, it's important to keep in mind that there's no objective definition of what's similar and what isn't. It always depends on the context and what your application needs to do. Here's an example. spaCy's default word vectors assign a very high similarity score to I like cats and I hate cats. This makes sense because both texts express sentiment about cats. But in a different application context, you might want to consider these phrases as very dissimilar because they talk about opposite sentiments. Now it's your turn. Let's try out some of spaCy's word vectors and use them to predict similarities. Combining statistical models with rule-based systems is one of the most powerful tricks you should have in your NLP toolbox. In this lesson, we'll take a look at how to do it with spaCy. Statistical models are useful if your application needs to be able to generalize based on a few examples. For instance, detecting product or person names usually benefits from a statistical model. Instead of providing a list of all person names ever, your application will be able to predict whether a span of tokens is a person name. Similarly, you can predict dependency labels to find subject-object relationships. To do this, you would use spaCy's entity recognizer, dependency parser, or part-of-speech tagger. Rule-based approaches, on the other hand, come in handy if there's a more or less finite number of instances you want to find. For example, all countries or cities of the world, drug names, or even dog breeds. In spaCy, you can achieve this with custom tokenization rules as well as the matcher and phrase matcher. In the last chapter, you learned how to use spaCy's rule-based matcher to find complex patterns in your texts. Here's a quick recap. The matcher is initialized with a shared vocabulary, usually NLP.vocab. Patterns are lists of dictionaries, and each dictionary describes one token and its attributes. Patterns can be added to the matcher using the matcher.add method. Operators let you specify how often to match a token. For example, plus will match one or more times. Calling the matcher on a doc will return a list of the matches. Each match is a tuple consisting of an ID and the start and end token index in the document. Here's an example of a matcher rule for golden retriever. If we iterate over the matches returned by the matcher, we can get the match ID and the start and end index of the matched span. We can then find out more about it. Span objects give us access to the original document and all other token attributes and linguistic features predicted by the model. For example, we can get the span's root token. If the span consists of more than one token, this will be the token that decides the category of the phrase. For example, the root of golden retriever is retriever. We can also find the head token of the root. This is the syntactic parent that governs the phrase. In this case, the verb have. Finally, we can look at the previous token and its attributes. In this case, it's a determiner, the article a. The phrase matcher is another helpful tool to find sequences of words in your data. It performs a keyword search on the document, but instead of only finding strings, it gives you direct access to the tokens in context. It takes doc objects as patterns. It's also really fast. This makes it very useful for matching large dictionaries and word lists on large volumes of text. Here's an example. The phrase matcher can be imported from spaCy.matcher and follows the same API as the regular matcher. Instead of a list of dictionaries, we pass in a doc object as the pattern. We can then iterate over the matches in a text, which gives us the match ID and the start and end of the match. This lets us create a span object for the matched token's golden retriever to analyze it in context. Let's try out some of the new techniques for combining rules with statistical models. Welcome back! This chapter is dedicated to processing pipelines, a series of functions applied to a doc to add attributes like part-of-speech tags, dependency labels, or named entities. In this lesson, you'll learn about the pipeline components provided by spaCy and what happens behind the scenes when you call NLP on a string of text. You've already written this plenty of times by now. Pass a string of text to the NLP object and receive a doc object. But what does the NLP object actually do? First, the tokenizer is applied to turn the string of text into a doc object. Next, a series of pipeline components is applied to the doc in order. In this case, the tagger, then the parser, then the entity recognizer. Finally, the processed doc is returned so you can work with it. spaCy ships with the following built-in pipeline components. The part-of-speech tagger sets the token.tag and token.pos attributes. The dependency parser adds the token.dep and token.head attributes and is also responsible for detecting sentences and base noun phrases, also known as noun chunks. The named entity recognizer adds the detected entities to the doc.ends property. It also sets entity type attributes on the tokens that indicate if a token is part of an entity or not. Finally, the text classifier sets category labels that apply to the whole text and adds them to the doc.cats property. Because text categories are always very specific, the text classifier is not included in any of the pre-trained models by default, but you can use it to train your own system. All models you can load into spaCy include several files and a meta.json. The meta defines things like the language and pipeline. This tells spaCy which components to instantiate. The built-in components that make predictions also need binary data. The data is included in the model package and loaded into the component when you load the model. To see the names of the pipeline components present in the current NLP object, you can use the NLP.pipeNames attribute. For a list of component name and component function tuples, you can use the NLP.pipeline attribute. The component functions are the functions applied to the doc to process it and set attributes. For example, part of speech tags or named entities. Let's check out some spaCy pipelines and take a look under the hood. Now that you know how spaCy's pipeline works, let's take a look at another very powerful feature: custom pipeline components. Custom pipeline components let you add your own function to the spaCy pipeline that is executed when you call the NLP object on a text, for example, to modify the doc and add more data to it. After the text is tokenized and a doc object has been created, pipeline components are applied in order. spaCy supports a range of built-in components but also lets you define your own. Custom components are executed automatically when you call the NLP object on a text. They're especially useful for adding your own custom metadata to documents and tokens. You can also use them to update built-in attributes like the named entity spans. Fundamentally, a pipeline component is a function or callable that takes a doc, modifies it, and returns it so that it can be processed by the next component in the pipeline. Components can be added to the pipeline using the NLP.addPipe method. The method takes at least one argument, the component function. To specify where to add the component in the pipeline, you can use the following keyword arguments. Setting last to true will add the component last in the pipeline. This is the default behavior. Setting first to true will add the component first in the pipeline, right after the tokenizer. The before and after arguments let you define the name of an existing component to add the new component before or after. For example, before equals NER will add it before the named entity recognizer. The other component to add the new component before or after needs to exist though, otherwise spaCy will raise an error. Here's an example of a simple pipeline component. We start off with a small English model. We then define the component, a function that takes a doc object and returns it. Let's do something simple and print the length of the doc that passes through the pipeline. Don't forget to return the doc so it can be processed by the next component in the pipeline. The doc created by the tokenizer is passed through all components, so it's important that they all return the modified doc. We can now add the component to the pipeline. Let's add it to the very beginning right after the tokenizer by setting first equals true. When we print the pipeline component names, the custom component now shows up at the start. This means it will be applied first when we process a doc. Now, when we process a text using the NLP object, the custom component will be applied to the doc and the length of the document will be printed. Time to put this into practice and write your first pipeline component. In this lesson, you'll learn how to add custom attributes to the doc, token, and span objects to store custom data. Custom attributes let you add any metadata to docs, tokens, and spans. The data can be added once or it can be computed dynamically. Custom attributes are available via the ._ property. This makes it clear that they were added by the user and not built into spaCy, like token.text. Attributes need to be registered on the global doc, token, and span classes you can import from spaCy.tokens. You've already worked with those in the previous chapters. To register a custom attribute on the doc, token, and span, you can use the setExtension method. The first argument is the attribute name. Keyword arguments let you define how the value should be computed. In this case, it has a default value and can be overwritten. There are three types of extensions: attribute extensions, property extensions, and method extensions. Attribute extensions set a default value that can be overwritten. For example, a custom isColor attribute on the token that defaults to false. On individual tokens, its value can be changed by overwriting it. In this case, true for the token blue. Property extensions work like properties in Python. They can define a getter function and an optional setter. The getter function is only called when you retrieve the attribute. This lets you compute the value dynamically and even take other custom attributes into account. Getter functions take one argument, the object, in this case the token. In this example, the function returns whether the token text is in our list of colors. We can then provide the function via the getter keyword argument when we register the extension. The token blue now returns true for ._.isColor. If you want to set extension attributes on a span, you almost always want to use a property extension with a getter. Otherwise, you'd have to update every possible span ever by hand to set all the values. In this example, the getHasColor function takes the span and returns whether the text of any of the tokens is in the list of colors. After we've processed the doc, we can check different slices of the doc, and the custom ._.hasColor property returns whether the span contains a color token or not. Method extensions make the extension attribute a callable method. You can then pass one or more arguments to it and compute attribute values dynamically, for example, based on a certain argument or setting. In this example, the method function checks whether the doc contains a token with a given text. The first argument of the method is always the object itself, in this case the doc. It's passed in automatically when the method is called. All other function arguments will be arguments on the method extension, in this case token text. Here, the custom ._.hasToken method returns true for the word blue and false for the word cloud. Now it's your turn. Let's add some custom extensions. In this lesson, I'll show you a few tips and tricks to make your spaCy pipelines run as fast as possible and process large volumes of text efficiently. If you need to process a lot of texts and create a lot of doc objects in a row, the NLP.pipe method can speed this up significantly. It processes the text as a stream and yields doc objects. It is much faster than just calling NLP on each text because it batches up the texts. NLP.pipe is a generator that yields doc objects, so in order to get a list of docs, remember to call the list method around it. NLP.pipe also supports passing in tuples of text context if you set as tuples to true. The method will then yield doc context tuples. This is useful for passing in additional metadata, like an ID associated with a text or page number. You can even add the context metadata to custom attributes. In this example, we're registering two extensions, ID and page number, which default to none. After processing the text and passing through the context, we can override the doc extensions with our context metadata. Another common scenario: sometimes you already have a model loaded to do other processing, but you only need a tokenizer for one particular text. Running the whole pipeline is unnecessarily slow, because you'll be getting a bunch of predictions from the model that you don't need. If you only need a tokenized doc object, you can use the NLP.makeDoc method instead, which takes a text and returns a doc. This is also how spaCy does it behind the scenes. NLP.makeDoc turns the text into a doc before the pipeline components are called. spaCy also allows you to temporarily disable pipeline components using the NLP.disablePipes context manager. It takes a variable number of arguments, the string names of the pipeline components, to disable. For example, if you only want to use the entity recognizer to process a document, you can temporarily disable the tagger and parser. After the with block, the disabled pipeline components are automatically restored. In the with block, spaCy will only run the remaining components. Now it's your turn. Let's try out the new methods and optimize some code to be faster and more efficient. Welcome to the final chapter, which is about one of the most exciting aspects of modern NLP, training your own models. In this lesson, you'll learn about training and updating spaCy's neural network models and the data you need for it, focusing specifically on the named entity recognizer. Before we get started with explaining how, it's worth taking a second to ask ourselves, why would we want to update the model with our own examples? Why can't we just rely on pre-trained models? Statistical models make predictions based on the examples they were trained on. You can usually make the model more accurate by showing it examples from your domain. You often also want to predict categories specific to your problem, so the model needs to learn about them. This is essential for text classification, very useful for entity recognition, and a little less critical for tagging and parsing. spaCy supports updating existing models with more examples and training new models. If we're not starting with a pre-trained model, we first initialize the weights randomly. Next, we call NLP.update, which predicts a batch of examples with the current weights. The model then checks the predictions against the correct answers and decides how to change the weights to achieve better predictions next time. Finally, we make a small correction to the current weights and move on to the next batch of examples. We continue calling NLP.update for each batch of examples in the data. Here's an illustration showing the process. The training data are the examples we want to update the model with. The text should be a sentence, paragraph, or longer document. For the best results, it should be similar to what the model will see at runtime. The label is what we want the model to predict. This can be a text category or an entity span and its type. The gradient is how we should change the model to reduce the current error. It's computed when we compare the predicted label to the true label. After training, we can then save out an updated model and use it in our application. Let's look at an example for a specific component, the entity recognizer. The entity recognizer takes a document and predicts phrases and their labels. This means that the training data needs to include texts, the entities they contain, and the entity labels. Entities can't overlap, so each token can only be part of one entity. Because the entity recognizer predicts entities in context, it also needs to be trained on entities and their surrounding context. The easiest way to do this is to show the model a text and a list of character offsets. For example, iPhone X is a gadget, starts at character 0 and ends at character 8. It's also very important for the model to learn words that aren't entities. In this case, the list of span annotations will be empty. Our goal is to teach the model to recognize new entities in similar contexts, even if they weren't in the training data. The training data tells the model what we want it to predict. This could be texts and the named entities we want to recognize, or tokens and their correct part-of-speech tags. To update an existing model, we can start with a few hundred to a few thousand examples. To train a new category, we may need up to 1 million. spaCy's pre-trained English models, for instance, were trained on 2 million words, labeled with part-of-speech tags, dependencies, and named entities. Training data is usually created by humans, who assign labels to texts. This is a lot of work, but can be semi-automated, for example, using spaCy's matcher. Now it's time to get started and prepare the training data. Let's look at some examples and create a small data set for a new entity type. While some other libraries give you one method that takes care of training a model, spaCy gives you full control over the training loop. The training loop is a series of steps that's performed to train or update a model. We usually need to perform it several times, for multiple iterations, so that the model can learn from it effectively. If we want to train for 10 iterations, we need to loop 10 times. To prevent the model from getting stuck in a suboptimal solution, we randomly shuffle the data for each iteration. This is a very common strategy when doing stochastic gradient descent. Next, we divide the training data into batches of several examples, also known as mini-batching. This increases the reliability of the gradient estimates. Finally, we update the model for each batch and start the loop again until we've reached the last iteration. We can then save the model to a directory and use it in spaCy. To recap, the training data are the examples we want to update the model with. The text should be a sentence, paragraph, or longer document. For the best results, it should be similar to what the model will see at runtime. The label is what we want the model to predict. This can be a text category or an entity span and its type. The gradient is how we should change the model to reduce the current error. It's computed when we compare the predicted label to the true label. Here's an example. Let's imagine we have a list of training examples consisting of texts and entity annotations. We want to loop for 10 iterations, so we're iterating over a range of 10. Next, we use the random module to randomly shuffle the training data. We then use spaCy's mini batch utility function to divide the examples into batches. For each batch, we get the texts and annotations and call the NLP.update method to update the model. Finally, we call the NLP.toDisk method to save the trained model to a directory. spaCy lets you update an existing pre-trained model with more data, for example, to improve its predictions on different texts. This is especially useful if you want to improve categories the model already knows, like person or organization. You can also update a model to add new categories. Just make sure to always update it with examples of the new category and examples of the other categories it previously predicted correctly. Otherwise, improving the new category might hurt the other categories. In this example, we start off with a blank English model using the spaCy.blank method. The blank model doesn't have any pipeline components, only the language data and tokenization rules. We then create a blank entity recognizer and add it to the pipeline. Using the addLabel method, we can add new string labels to the model. We can now call NLP.beginTraining to initialize the model with random weights. To get better accuracy, we want to loop over the examples more than once and randomly shuffle the data on each iteration. On each iteration, we divide the examples into batches using spaCy's mini batch utility function. Each example consists of a text and its annotations. Finally, we update the model with the texts and annotations and continue the loop. Time to practice. Now that you've seen the training loop, let's use the data created in a previous exercise to update a model. When you start running your own experiments, you might find that a lot of things just don't work the way you want them to. And that's okay. Training models is an iterative process, and you have to try different things until you find out what works best. In this lesson, I'll be sharing some best practices and things to keep in mind when training your own models. Let's take a look at some of the problems you may come across. Statistical models can learn lots of things, but it doesn't mean that they won't unlearn them. If you're updating an existing model with new data, especially new labels, it can overfit and adjust too much to the new examples. For instance, if you're only updating it with examples of website, it may forget other labels it previously predicted correctly, like person. This is also known as the catastrophic forgetting problem. To prevent this, make sure to always mix in examples of what the model previously got correct. If you're training a new category website, also include examples of person. spaCy can help you with this. You can create those additional examples by running the existing model over data and extracting the entity spans you care about. You can then mix those examples in with your existing data and update the model with annotations of all labels. Another common problem is that your model just won't learn what you want it to. spaCy's models make predictions based on a local context. For example, for named entities, the surrounding words are most important. If the decision is difficult to make based on the context, the model can struggle to learn it. The label scheme also needs to be consistent and not too specific. For example, it may be very difficult to teach a model to predict whether something is adult clothing or children's clothing based on the context. However, just predicting the label clothing may work better. Before you start training and updating models, it's worth taking a step back and planning your label scheme. Try to pick categories that are reflected in a local context and make them more generic if possible. You can always add a rule-based system later to go from generic to specific. Generic categories like clothing or band are both easier to label and easier to learn. Let's look at some of these problems in context and fix them. Congratulations, you've made it to the end of the course. Here's an overview of all the new skills you learned so far. In the first chapter, you learned how to extract linguistic features like part-of-speech tags, syntactic dependencies, and named entities, and how to work with pre-trained statistical models. You also learned to write powerful match patterns to extract words and phrases using spaCy's matcher and phrase matcher. Chapter 2 was all about information extraction, and you learned how to work with the data structures, the doc, token, and span, as well as the vocab and lexical entries. You also used spaCy to predict semantic similarities using word vectors. In Chapter 3, you got some more insights into spaCy's pipeline and learned to write your own custom pipeline components that modify the doc. You also created your own custom extension attributes for docs, tokens, and spans, and learned about processing streams and making your pipeline faster. Finally, in Chapter 4, you learned about training and updating spaCy statistical models, specifically the entity recognizer. You learned some useful tricks for how to create training data and how to design your label scheme to get the best results. Of course, there's a lot more that spaCy can do that we didn't get to cover in this course. While we focused mostly on training the entity recognizer, you can also train and update the other statistical pipeline components, like the part-of-speech tagger and dependency parser. Another useful pipeline component is the text classifier, which can learn to predict labels that apply to the whole text. It's not part of the pre-trained models, but you can add it to an existing model and train it on your own data. In this course, we basically accepted the default tokenization as it is, but you don't have to. spaCy lets you customize the rules used to determine where and how to split the text. You can also add and improve the support for other languages. While spaCy already supports tokenization for many different languages, there's still a lot of room for improvement. Supporting tokenization for a new language is the first step towards being able to train a statistical model. For more examples, tutorials, and in-depth API documentation, check out the spaCy website. Thanks so much for taking this course. I hope you had fun, and I'm excited to hear about all the cool things you end up building with spaCy.